In the first video for chapter 16, we saw how we could derive the equations for the mass spring system. And now we want to take a look at solving the equation for the mass spring system. Here's the description of the variables that we are using. The m is mass, which would be a constant. The lambda is the friction constant, and the kappa is the spring constant from Hooke's law. The F is the external force, if there is such a thing. Now we'll be solving our equation based on the assumption that there is no external force. So we have a second order equation, homogeneous with constant coefficients. Now the mass m and the spring constant kappa are always positive constants. And the lambda is referred to as the damping constant. Now it could be that the damping constant is 0, in which case there is nothing dampening the motion, or it could be that the damping constant is positive, in which case there is something inhibiting the motion. Now we'll first investigate the undamped system. That's where the lambda is 0. Well, just like we did in the earlier chapter, we can solve the characteristic equation, and we come up with the two solutions, plus or minus square root of negative kappa over m. Well, remember, kappa and m were both positive constants. That means that these will be complex numbers. So we will have the solution plus or minus square root of kappa over mi. So we will refer to the quantity square root of kappa over m by the name omega naught, omega sub 0. You'll see the significance in this later. And so the roots come out to be plus or minus omega naught I, which means that we can write our solution with the cosine omega naught t and sine omega naught t. And the e's would disappear since lambda is 0. Now there is another way that's commonly used for writing the answer to that differential equation, and that is derived from considering the point that's given as C1 comma C2, where the C1 and the C2 are the two constants derived in the solution of the differential equation. So we're going to call the distance from the origin to the point C1 comma C2 as capital A, and you'll see some of the significance of this shortly, and then the angle up from the positive x-axis as the phi. So the x and the y can be given as a cosine phi and a sine phi. That means that the distance a, which is the square root of the x squared plus the y squared, would give us the a cosine phi times the cosine omega naught t plus a sine phi sine omega naught t, which we can factor out the a, and you can see the stuff in parentheses, cosine phi cosine omega naught t plus sine phi sine omega naught t is a trig identity. That's the identity for the difference of two angles. So we could write the solution to the undamped system either as y equals some constant cosine omega naught t plus some other constant sine omega naught t, or we could write the solution as y equals some constant cosine of the quantity omega naught t minus phi. Now they each have their usefulness in certain situations. The a here is the amplitude, the number in front of a trig function, gives us the amplitude. And the significance behind the omega naught t minus phi is that if we use a p sub 0 for the time it takes for one cycle, we can take a look at the time from omega naught t naught minus phi to omega naught t naught plus p naught minus phi, and do the calculation ending minus beginning and come up with the omega naught times p naught. Well, now that's got to be equal to 2 pi, since it's a cosine function and the period of cosine is 2 pi, which means the significance of the omega naught is the period p naught is 2 pi divided by that quantity. And we could have told that from the very beginning by the position of the omega naught in the cosine function. However, this is the time for one cycle. If we flip that, we get the number of cycles per unit time, which is called the frequency. So P naught is referred to as the natural period. V naught is referred to as the natural frequency. So here's an example where we're asked to find all of these quantities. Well, from the earlier presentation, F equals kappa L from Hooke's law tells us that we can find kappa by doing F divided by L. Well, it says in the problem F is 2 and L is 1/2 of a meter, so that comes out to be kappa equals 4. And then from the previous, we found omega naught to be the square root of kappa divided by m, which we just found kappa. We can divide that by m and do the square root. And we just derived a formula for the frequency. Omega naught divided by 2 pi would give us 1 over 4 pi. And the period would just be the reciprocal of 1 over 4 pi, or 4 pi. And we've already done the work for solving this, so we won't start from the very beginning. Just recognize that our solution has this format and the other one, which we'll get to from this one, like we developed it. So to find the constants, we'll substitute our y0 equals 0, and that gives us C1 equals 0. We'll substitute our y prime 0 equals 2, and that gives us our second constant. So our differential equation then would be a 0 cosine 1/2 t plus 4 sine 1/2 t in that format. Now we also developed the expression for a, which is the square root of the c1 squared plus the c2 squared, which in this case comes out to be just a 4. And we saw that the c1 was a cosine phi, which means that the cosine of phi is c1 divided by a, and that c2 is a sine phi, and so sine phi is c2 divided by a, which after we have found a, we can find the phi by finding an angle whose cosine is 0 and whose sine is 1. Well, the angle whose cosine is 0 and sine is 1, or at least the smallest positive angle of that sort, is just the pi over 2. So we would come out with the two equations 4 sine 1/2 t, or 4 cosine 1/2 t minus pi over 2. The graph of each of these obviously would be identical. Now, damped systems are primarily important just in the knowledge that it is a damped system and what sort of damped system it is. Now, if we solve this equation, you notice from the characteristic equation we end up with this. Now, the quantity lambda squared minus 4 kappa m is of special significance because that gives rise to these three situations. We could have a negative value, 0, or a positive value for that. If it's a negative value, then lambda is less than 2 times the square root of kappa times m, and we call this underdamped. If the discriminant, lambda squared minus 4 kappa m, is 0, we have lambda equal to 2 square root of kappa times m, which is a critically damped system, and then an overdamped system. Now, I've drawn a representative graph of each of these to help illustrate what we mean by underdamped, critically damped, and overdamped. Notice that on the underdamped system, you still have an oscillation happening, only it's getting less and less each time. But in a critically damped system, it begins like it's going to oscillate, but there's nothing happening after that. In an overdamped system, it never even tries to oscillate. You let go of the weight and it just plummets. Now, considering an underdamped system where lambda squared minus 4 kappa m is negative, if we did our solution by finding the characteristic value, the value of r in the characteristic equation, we come up with this. Now here we have the lambda over 2m, we'll call that by the name alpha, and then we have the rest of it, which we'll call by the name omega. And our solution would look like this. Now again, you notice the minus is taken care of here. However, this is a underdamped system where the discriminant is negative. So you still have a complex solution. Now, in a critically damped system, the lambda squared minus 4 kappa m is 0, which means our characteristic equation would have the single duplicated root negative lambda over 2m. And we found earlier that we could use lambda as 2 root kappa m, and so substituting that, we get just the negative of root kappa over m. Now remember, that's a root twice. It's a duplicated root. It just is a negative kappa, root kappa over m. So, using alpha to be just the root kappa over m, we end up with the two different solutions given by C1e to the negative alpha t and C2t e to the negative alpha t. And finally, in the overdamped systems where the discriminant is positive, we again end up with the two roots, only this time we're going to factor out the negative 1 and call alpha and beta as our two distinctive roots. And so we'll end up with the C1 e to the negative alpha t and C2 e to the negative beta t as our two solutions. Now in this example, we're asked to categorize the system given by these values of kappa, m, and lambda. So, using our discriminant, lambda squared minus 4 kappa m, we get a negative value. Now the negative value means that it's underdamped. Now we're going to continue on and solve the system. Now we've already done all of the work. It should be on a handout that you'll be given in class. and we can just substitute and write our equation. Now we're also asked to draw the graph of that, so we need to find the constants by plugging in the given values. Y0 equals 0 gives us C1 equals 0. Y prime 0 equals 1 gives us C2 equals 1/3. So our equation would look like this. And like in the previous example, we want to take our square root of lambda squared minus 4 kappa m and determine if the lambda squared minus 4 kappa m is positive, negative, or 0. So we substitute in and we get 0. So it's critically damped. And like in the previous example, since we've already done all of the work for solving a differential equation with a kappa, m, and lambda given, we'll just use what we came up with. We're going to use the alpha equals square root of kappa over m, do the calculation for alpha, substitute it in, and there's our general equation. Now we need to find the specific equation from the initial conditions. So we'll go ahead and do the derivative, use y0 equals 1 to find constant 1, use y prime 0 equals 2 to find constant 2, and then draw the graph